Okay, so we're still very much in the background stages of NMR, and this is, background theory. I will say it's not my field at all, and I have a difficult time even caring about it, but it does add some valuable insight. So I've collected some comments from this section in the book, and we're going to go through them, but we're only going through them to help understand the deeper things. All right, so do your best to follow along here. And I'm going to do my best to sound interested myself. So we're going to talk now about acquiring. How do we get an NMR spectrum? This is proton NMR spectroscopy we're interested in. Okay, so NMR requires a strong magnetic field, which we said before in previous conversations. The strength of the magnetic field affects the energy gap, right? So if we've got some energy gap between the alpha spin state and the beta spin state, some energy difference between those two, that corresponds to a field that will have this difference in energy, all right? Which the numbers, if you can bear with me, the numbers don't really matter as much as the principle matters. That this energy difference is going to come from an energy difference of an external magnetic field, and that is going to be the energy of this photon right here, right? So let me get my red marker here. The photon here, that has a particular energy that gets absorbed. That is that energy difference, okay? And it's going to, for the magnetic field, it's going to correspond to the spin and so on, all right? So we have this external field. That's the energy that the energy difference is what we're interested in. Now, here's some things with which I just don't think about this stuff very often. Let's walk through it. A strong magnetic field is created, and here's how it's created, when a high current is passed through a superconducting material at low temperatures. So we're talking, close to liquid helium, okay? And so if we get high current through liquid helium, then we can get a strong magnetic field. So you can see why these apparatus are expensive. The greater the current, of course, the greater the magnetic field. And we're going to analyze this with something called pulse Fourier transform. A brief pulse of radio energy, all relevant wavelengths, is used to excite the sample. Each of the atoms is excited, and then every one of them is excited, and then it relaxes. And when it relaxes, it emits energy. Okay? The emitted energy is recorded by the apparatus through something called a free induction decay, FID. Now, the FID contains all of the information for each atom. We treat it with a mathematical technique called Fourier transform, and it separates the signals out. We oftentimes are going to do a bunch of them so we get a cleaner separation. We do a bunch of them, and then we average them together. Before we analyze them, we've got to make sure, let's talk, that's sort of how we acquire it. Let's talk about the analysis here. Before we analyze it, they need to be in liquids that are neat, and that is, in other words, they don't have any water in them, or a deuterated solvent, which means that it doesn't have any free hydrogens in it. Okay, deuterated means like your water might be DOD, right, instead of H2O, right? Why would H2O be a problem? Because it's got a bunch of protons in it, right? And we want to make sure we're not confusing the spin flips of the solvent with the spin flips of the sample that we're trying to analyze. Okay, sample is placed in a magnetic field, and the tube is spun. Right, it's a little tiny tube. Well, it's close to actual size. A little tiny tube, and it's spun really fast. Right, and we do that to take care of field variations, magnetic field variations, and tube imperfections. All right, and that's how we acquire a spectrum for a proton NMR.